Hello everyone and welcome back to the course. In today's lesson, we are going to talk about x-intercepts of polynomials. In other words, we're going to talk about roots of polynomials. A root or a zero of a polynomial p of x is a value x null in the domain of the polynomial such that p of x null is equal to 0. For instance, if we take the polynomial p of x equal x squared minus 7x plus 10, we notice that p of 2 and p of 5 are both equal 0. Thus, x equal 2 and x equal 5 are roots of the polynomial. We can also notice that x equal 2 and x equal 5 are both x-intercepts of the polynomial p of x. Something that we can notice about this particular polynomial and its roots is that p of x can actually be written as x minus 2 times x minus 5, meaning x minus the first root times x minus the second. Actually, in general, if we have a polynomial p of x of degree n and x null is a root of that polynomial, then p of x can be written as x minus x null times another polynomial q of x, where the degree of q of x is equal to the degree of p of x minus 1. Now, let us consider the polynomial p of x equal x squared plus 2x plus 1. Then, we notice that p of minus 1 is equal 0. We only need to substitute such a value in order to be able to see that this is actually satisfied. Then, by the previous result, we know that p of x can be written as x minus the root, and as our root is -1, it will be x plus 1 times another polynomial which degree is 1 less than the degree of p of x. Thus, that polynomial has to be written as ax plus b. Now, p of x is x squared plus 2x plus 1. And if we apply distributive property, we get that this is equal to ax squared plus a plus b times x plus b by applying distributive property to the expression x plus 1 times ax plus b. We have a polynomial equation, and two polynomials are the same if they're equal in coefficients. So if we have that x squared plus 2x plus 1 is equal to ax squared plus a plus b x plus b, then a has to be equal 1, a plus b has to be equal 2, and b has to be equal 1. So, by knowing that a is equal 1 and b is equal 1, we can actually substitute those two values in the expression ax plus b, for knowing that such expression is actually x plus 1. Thus, the polynomial p of x can be written as x plus 1 times x plus 1. Thus, p of x is equal to x plus 1 squared. Something that we can notice from the previous example is that the polynomial p of x had a root which was x equal -1. And we also notice that p of x could be written as x minus -1 squared, meaning x plus 1 squared. Now, every time a polynomial p of x has a root x null such that p of x can be written as x minus x null to the power of m times another polynomial q of x, then we say that x null is a root of multiplicity m. And the degree of the polynomial q of x is equal to the degree of the polynomial p of x minus m. The multiplicity of a root can say a lot about the behavior of the polynomial at such a point. If the root has a multiplicity which is odd, then the polynomial crosses the x-axis. But if the multiplicity of the root is even, then the function is tangent to the x-axis at the root. For quadratic functions, we can use the quadratic formula for finding the roots of such polynomials. If the expression b squared minus 4ac is greater than 0, then such a polynomial is going to have two real roots. But if it is equal to 0, then we are going to obtain one root with multiplicity 2. But if such expression is less than 0, then the polynomial has complex roots. And we're going to see about that in the next lesson. In the meantime, try to find the roots of the following polynomials. And as always, see you in the next lesson.